Welcome back. We're going to do a video presentation now on series circuits. Okay, so a few things to mention before we start. This particular circuit or practical experiment is going to verify the following laws of series circuits, which we've already done the theory on. With the voltage, as Kirchhoff's voltage law tells us, the sum of the voltage drops equals the supply voltage. So the voltage drop across V1, V2 and V3 is going to equal the total supply voltage. The current through the circuits are going to be the same. So the current is the same in all parts of a series circuit, and the total equivalent resistance is going to equal the addition of the three resistors, in this particular case R1, R2 and R3. There's some values there to write down as you go through it. Your facilitator will give you those values. Flip over, we've got a risk assessment. You go through that as well. Super risk class and control measures. Now there's a couple of different ways of reading the resistances with an analog multimeter or digital multimeter. Either meter that you use, ensure that you zero or null the meters out. Obviously calibrate the scale on the analog multimeter, or null your multimeter reading if possible, or make sure that subtract the resistance to the leads. Once again, you would have done that in class hopefully at some point. Calculate the equivalent resistance. Okay. We'll turn this page over. We'll jump straight into it. R1, R2 and R3. My three resistors is a 12 ohm, a 10 ohm and an 18 ohm. So that's 12 ohm, 10 ohm and 18 ohm. So RT is equal to R1 plus R2 plus R3, which is equal to 12 plus 10 plus 18, which is equal to 10, 20, 30, 40 ohms, or thereabouts. Let's connect that up and see if that works. So that resistor that just connects to that one, and the 10 ohm, we can actually wire it up probably the same way as this here anyway. We'll do it like that. This will help our practical experiment. And the third resistor and the first resistor, which is here. So this is my resistor, R1, R2, R3. This is R1, R2 and R3, and they're connected in series. And that's the total resistance. So if I was to get a multimeter, and I'll grab my multimeter there, and I'll plug them in. We measure the resistance there of 40 ohms. And there was one thing I did mention that I have not done, and I said ensure on the previous page that you calibrate or null your meter. So I'll do that for the purpose of the exercise. Plug the two leads in together, and the leads are reading 0.1 of an ohm. This particular meter, the Agilent, has a null button, so I can null that. So now there's no resistance taken in those leads, and I'll plug them in, and now we've got exactly 40 ohms, which is exactly what we've got, 40 ohms. Okay, moving forward, I can wire that circuit. We're on the next part of it. So we've already got our three resistors connected in series. So we'll go back into the power supply. So the idea of this is to measure the current and the voltage drops across the circuit. Okay, so we go from power supply into a switch. We bypassed the fuse from the previous experiments, as we're all aware that the fuse had that workplace health and safety issue that was exposed the whole time. So we can obviously, the power supplies are current limited, so we're pretty safe not to use a fuse in this particular respect. So we're going to go out of the power supply into a switch. So I'll unplug this multimeter for now, and I'll come grab a switch. So go out of the power supply into the switch, out of the switch into the ammeter. So out of the switch into the positive of the ammeter, out of the ammeter into the first resistor, so out of the ammeter, and I'll stick with my colour coordination which we've been doing over these video practicals, out of the negative out of the ammeter into the resistor. Resistor 1, resistor 2 and resistor 3. So 1 through that, into the third resistor, back into the negative of the power supply. Just like that. Now the other thing, we've got a voltmeter, which is at this particular stage is measuring across the power supply. So my voltmeter here, my voltmeter is going across the power supply, as per pictorial. So we'll go to the volts, goes into the red, and the black, negative, goes into the negative or the black terminal up here. Put that in volts, and we've got that in amps. Okay. Now before I turn that on, we're going to select a supply voltage as given by the instructor there. So let's have a look. If I was using our Ohm's law calculation, if I was to give a supply voltage of say 10 volts, so supply voltage volts, my resistance calculated and measured is equal to 40 ohms. Therefore, my current is equal to, holding my finger over the I is equal to V over R. Current is equal to V, 10 divided by R, which is 40, which is equal to, for those of you that just to trust the old calculator, 10 divided by 40 is equal to 0.25 of an amp. 0.25 of an amp. Or if we jump 3 places, if we discussed, 1, 2, 3, 1, 2, 3, be 250 milliamps. This particular meter here measures in amps though. So I'm going to turn the power supply on, adjust to 10 volts, turn the switch on, and I should be reading 0.25 of an amp, and my voltage should be 10 volts. Let's have a look. Turn the voltage up to 10 volts. So I'm at 10 volts, turn the switch on, and there we've got it. 10 volts, or 10 volts here on the meter, and we've got 0.25 of an amp being current flowing in that circuit. That works quite well, so let's confirm that part of it. Now the next part of this particular prac goes into, let's measure the current, that's the total current. That's the total current that we've measured as per there. Then we're going to say if we were to put the ammeter, move the ammeter from the supply and just measure the current through R1, through this resistor here, R1, what current would we see? Okay, let's have a look. So remember with current, we turn the power off. Okay. The first thing with current, the easiest way to remember current is you always only use one lead with the ammeter. You can't mess it up that way. So if I unplug one lead and one lead only, there's my circuit wide. So my ammeter, I've got one lead in my ammeter. Okay, so there's my circuit without an ammeter. Most important always have one lead in the ammeter, not two. Okay, so goes into the series circuit. There's no current meter in that, but we can see there it's a simple series circuit flowing through. Now what I want to measure with this ammeter is the current flowing through this resistor. So there's current flowing through this resistor. So the first thing I do is I unplug that resistor. So then I plug the ammeter into that resistor. So the current's flowing through that resistor into the ammeter, and the lead I unplugged plugs back into the ammeter. So it's flowing through that resistor, into the ammeter, out of the ammeter, back into the circuit. And that's the voltmeter, which is just across the circuit. So I'll turn that back on. Go on there. So I've got 0.25 of an amp flowing through that resistor, R1. So that's where my ammeter is at the moment, and I've still got 10 volts. So I'll turn that back off. Okay. Remember the workplace health and safety requirement, just want one lead in the ammeter, is to make sure you never unplug a circuit when current's flowing through it. Okay, so I'll unplug, this is the second resistor, so I'm going to measure the current through R2, so I2. So the ammeter plugs into the resistor, the current's flowing through the resistor into the ammeter, and then one lead plugs back in, back where it went. So So now I'm measuring the current through this resistor. Once again, I'll turn it back on. And we can see we've still got 0.25 of an amp, 10 volts. So exactly the same. So I1 is the same, so we should write this down. So I total was equal to 0.25 of an amp. I1 is equal to 0.25 of an amp. I2, which is through resistor 2, is equal to 0.25 of an amp. And the theory is, just turn that off, same thing again, unplug, keeping in mind I've got one lead, unplug, this plugs into, so the current goes through the resistor into the ammeter, back out, back to home, and I3 equals 0.25 of an amp. So it's exactly this, therefore, as per our theory content, IT is equal to I1, which is equal to I2, which is equal to I3. That is, current is the same. A series circuit. Definitely tick that box from one of the objectives. The other thing we're going to consider is the voltage drops throughout the circuit. Just found the other page, right there. The voltage drops was Kirchhoff's voltage law. These voltage drops should add up to equal the supply voltage. So we've confirmed that first rule there. Okay, so I'll turn that off. Now I'll put the circuit back to in this particular case, we've got 1 voltmeter, okay, which is the supply voltmeter, and we haven't got an ammeter. So I'll take out the ammeter. So keep in mind, just want one lead. That's my ammeter gone. Okay, so we've got 3 resistors now, 1, 2, and 3. So as this is a multimeter, I can use it as a multimeter as well, the fleet. So I put on volts, okay, and now I move the lead from the amps over the volts. This is my voltmeter. So we should find that the supply voltage VT is equal to V1 plus V2 plus V3. So VT is equal to V1 plus V2 plus V3. Okay, so what V1 is equal to on V1? So with voltage, we can actually do it while the power's on. That is to say, because we're going across a component, we're not breaking the circuit, we can just plug it in while the power's on. So we've got 10 volts, so let me plug this one in. And across this particular resistor here, the 12 ohm resistor, V1 I've got 2.89 volts. Plus V2, like that, plus V2. Get a little bit messy with the leads, but having said that, still see the concept, 2.5 volts across that resistor. So it's 2.5 volts, 2.53, I guess we could probably try a bit more accurate, plus V3. V3. Oh, there you go, that's a good reading. Negative 4.6 is equal to 4.61 volts. Now that's negative only because I have the reads logged around the wrong way. That's the positive side. I'll just show you that. 4.6. So it doesn't matter on a digital multimeter where that would be of concern. We had an analog multimeter that one had a needle would have went the wrong way. It would have not been very healthy for the meter movement. Okay, so these 3 voltages, do they add up to the supply voltage? Supply voltage of 10 volts. Let's bring the calculator into play and have a look. We've got 2.89 plus 2.53 plus 4.61. 10.03. So VT is equal to 10.03 volts, which is almost exactly what it is, 10 points. So therefore, once again, we've proven Kirchhoff's voltage law, KVL, that concludes the practical.